All right, guys, we got a handful of ideas that I want to talk about today. First one is going to target, I sent out a video yesterday that deals with one example like this, so I want to make sure that we all see this. It's not a difficult concept, but WebAssign, for some reason, doesn't target graphing logarithms, and to be honest, I don't think WebAssign does a great job of graphing really anything, because it's more of a recognition thing for you, okay? But if we can recognize the behaviors and the things that are supposed to be occurring because of certain components in our equations, hopefully that's enough, and that we can then take that information and then plot those points. We've got some options when graphing a logarithm. I'm going to write something down here that I don't want you to write down because I just want to kind of prove a point to you, okay? We've talked about how we find the inverse of a function, right? Find the inverse of a function. We can do one of two things. We can either solve for x right away, isolate x, and then interchange the variables, or we can interchange the variables first, and now solve for y, okay? I'm going to do that. So basically, if I was going to solve for y, okay, I have to isolate, and this is something we'll practice and talk about quite a bit. I'm going to apply my definition of a logarithm, okay, to turn into an exponential. I have to isolate that part first. It's kind of like dealing with square roots and things of those natures. If I have a root equation, don't I have to isolate the root before I start squaring things? Okay, so I have to isolate that before I start taking the inverse. Okay, so I'm going to add 4 to both sides, because x plus 4, gracias, is equal to -3 log base 4 of y plus 2. Okay, I'm now going to divide both sides by -3. So x plus 4 over -3 is equal to log base 4 of y plus 2. Now I've isolated, now I can use the definition of the logarithm, and I can change this to an exponential. So this base raised to that exponent. So I have 4 raised to the x plus 4 over -3 is equal to y plus 2, right? Can I subtract 2 then? And there's my exponential. Okay? Now, what I could do is I could find 3 points that exist on that exponential. We know 0, 1, 1a, and -1, 1 over a are on 4 to the x. But then we have to think about, okay, how does that -3 in my exponent affect those points? How does that plus 4 in my exponent affect those points? And how's my -2 affect those points? And do essentially the transformations of those. Does that make sense? And then I have 3 points that are on that exponential. Well, its inverse is the blue equation we started with, right? So I can flip those ordered pairs, flip their x's and y's, and graph those, and now I've got points for the exponent, or for the logarithm. I think that's messy. I think that that's hard because of what this thing here is going to do to your x's and y's. Okay? So, what I prefer to do is this. Recognize what your parent logarithm is. Our parent logarithm is log base 4 of x. Okay, if I graph these two things, let's graph this one without the negative real quick. Are they kind of the same behavior? Yeah. The negative just flips them, right? Okay. And even if I just get rid of the 3, that's even more kind of resembling one another, right? And we see that's just a movement left and down. So my parent function, I'm going to identify first. All right. And then I know if y equals log base 4 of x. Now I'm going to go through that inverse procedure with this. So I replace x and y. So it's going to give me x equals log base 4 of y. And now I'm going to solve for y. Well, that's going to yield 4 to the x equals y. Is that okay? That is easier, guys, to kind of get the ball rolling here in regards to what points I need to transform. those points, or that function, I know 3 points that exist on every single exponential. They are 0, 1, 1, a, and -1, 1 over a, right? That's what we talked about the first day that we did these exponentials. What is the a value right here? 4, right? Okay. So I got 1, 4, and I get -1, 1/4. Those are 3 points off of y equals 4 to the x. So let me do this real quick. Just kind of explain to her. You tell me what I did. Those points should be on the what of y equals 4 to the x? The inverse. And the inverse of 4 to the x is log base 4 of x. Does that make sense, everybody? So those 3 points are 3 points that come from that parent function right there. Is that all right? So those are the ones I'm going to start with. 1, 0, 4, 1, 1/4, -1. And I'm going to go through the horizontal transformation, the vertical or horizontal stretches, and the reflections, and a vertical shift with these 3 points. Okay? So, horizontal shift is that thing right there, right? So how many units and in what direction am I going to be moving every single one of these points? To the left 2. So if I'm going to the left 2, doesn't that mean I have to subtract 2 from that value? So it gives me -1, 0. I subtract 2 from that value, so it gives me 2, 1. And I subtract 2 from that value, it gives me -7/4, -1. Is that all right? So those points right now, guys, would be on the, if I were just to look at log base 4 of x plus 2, those 3 points are on that curve. Okay? Now, so we did that. Now we got to do stretching. And we can actually do these 2 things together. So the stretch is what number? The 3. And the reflection is x-axis reflection, right? So that just makes my y's that were positive negative and the ones that were negative positive, right? So essentially all I'm going to do is go through and multiply every one of my y values by a -3 here. And you see how this one was positive, became negative, this one was negative, became positive, right? So that's taking care of the reflection. So this would be -3, all the points here in black would be -3 log base 4 of x plus 2. I now need to do the vertical stretch, right? Or sorry, vertical shift. So that -4, how do I address that with these points? It's going down 4, right? So all the y values are going to lose 4 units. And now I would graph those 3 points. Those 3 points they start off as my parent function, logarithm base 4 of x points. And then I did those, 1, 2, 4 transformations to them. Okay? So if I go -1, -4, 2, -7, and -7/4, -1. Those 3 points, connecting with a smooth curve, produce then that logarithm that I'm trying to find, right? Okay. I think that, even though that's a little time consuming, I think that's the best approach for developing the equation of a logarithm. Okay. So there's a video in your email that I sent yesterday doing another example of that. Like I said, WebAssign doesn't necessarily target questions that difficult. They do ask you to take some basic, you know, if I have log, like base 4 of x plus 2, they ask questions, okay, if I had something like, so if I have the red one, okay, how does the green one relate to the red one? And you answer that it's a shift 2 units to the left, right? or it gives you this red one as like your starting picture, and then there's 4 options down below. It says pick the one that is log base 4 of x plus 2. So then you would find the one that obviously looks like that. They ask those types of questions, but they don't involve like 3, 4, 5 transformations all at once. But I think we should have the ability to do those things. The next thing I want to talk about, and we did kind of hit on this yesterday, but if I take, I'm just going to write a to the x, where a is just my base. I don't want my base to be 1, so I'm just going to start at 1.1, and we'll go 50. Okay. If I do that, look at that curve. Look at that exponential. Okay. They all kind of show the same behavior, right? It just happens that the, if I put a point on here, right there, and look at the y value of that. So let's say y of a. Just look at that 3.8 number, 89 number right there. The only thing that happens is that value gets a lot bigger, a lot faster when my bases grow, correct? Does that make sense? Okay. But the behavior is very similar. It's exponential. We still have a what down here. What is this line, y equals 0? What is that line for my exponential? And any one of these exponentials. It's an asymptote, right? It's a horizontal asymptote. And it behaves in a nature in which we do not ever cross it, okay? If we were to set, does 1.8 to the x ever equal 0, okay? And we'll learn how to solve this equation later this week, maybe tomorrow, late tomorrow or Monday. We'll talk about how we solve that equation, and we'll see that we get something that doesn't make any sense, okay? So we don't cross our horizontal asymptote. If that is an exponential, okay, and a logarithm is its inverse, so a logarithm is going to be the reflection across that dotted line, right? Y equals x. So if I reflect that curve across there, so let's see here, let's change that one's color. Can't. So I'm looking at that. That is my logarithm. Okay, now it's written as a parametric equation. We'll talk about that later, a parametric curve. But that is my logarithm. Okay. When I flip this thing over y equals x, when I flip the exponential, okay, all of the parts of that graph that explain the graph's behavior, such as the asymptote, okay, also get flipped. Okay. So if I were to graph that line y equals 0 and reflect it over y equals x, you get that green line, right? Does that make sense? And that now is a what for our logarithm? A vertical asymptote, okay? So, logarithms have vertical asymptotes, meaning they have domain issues. Does that make sense? Okay, when we talked about our exponentials, domain was all real numbers. It was the range that was 0 to infinity, right? Not including 0. Well, when we reflect, when we flip over the line y equals x, or find the inverse, remember domains and ranges switch spots? The range becomes the domain becomes the range, right? So here, the domain is now 0 to infinity, excluding 0, and our range is all real numbers. So what does that mean to me? It means when I ask the question, what is the log base A of any negative number? It's going to give me something undefined. Does that make sense? Okay? Because there is nothing over here. There are no inputs that you can use as an x being negative that is going to yield a y value that is on that blue curve. Okay? That's something to remember as we move on to solving equations. Remember, all this stuff that we're talking about, there's 4 sections here at the beginning of chapter 4 that are all targeting learning properties and skills so that we can target solving equations. Okay? To have logarithms in them and have exponentials in them. At some point, we will do some work where we get multiple solutions for x, okay, inside our logarithmic equation. When we substitute those back in, if we get a negative argument, we know that's not a solution because of the domain cannot be a negative number. Does that make sense? Okay. So that's something we'll come back to in a little bit, but I need you to understand that you cannot take the log of a negative value. All right, so that gets us to revisit a couple properties, and I got to find out. I've got so many PowerPoints open here. I don't think I want this one open. Yeah, get rid of this one. What is our base for our number system? What's the base for binary? You guys know what that means? What? Binary is 0 and 1, right? Those are only two values that exist in the binary system, okay? So there's only two values. It's a base 2 in that system, right? What base do we use? What is the base of the metric system? 10. Okay. So we use, our number system is base 10, right? Everything that we ever deal with is multiples of 10 or raised powers of 10. Okay. We have 10 values in our number system that get repeated over and over and over again, right? When we look at it, so we know like and I use the metric system because it is powers of 10, and the metric system is a very easy thing to work with and manipulate. The English system, like dealing with, or the imperial system, I believe, it's like feet and inches and miles, and they're all different units, right? All different values, place values, and all that kind of stuff. But we use a base of 10. That is common to us. Does that make sense? Okay. If you go back to, like, does anybody know why, like, clocks, like, minutes are 60 minutes in an hour, 60 seconds in a minute? Why it's that way? Why it's not? Why don't they choose, like, 100? Anybody know? Ancient clock. Yeah, it goes back to the Babylonians. Okay. The Babylonians had a system that was based off the number 60. Okay, that was their base. Okay. So when they started kind of dealing with time, they were using a base 60. That's why there's 360 degrees in a circle. Okay. Because some work with hexagons and the circumscribed circle, the hexagon, all that kind of stuff. They knew with their system they had 6 multiples of 60 gave us 360. Okay, which just talks about how throughout history different groupings or different cultures use different bases. Right. We are now using base 10. It's the most common thing for us to do. You guys ever heard of the phrase or the word hexadecimal? Yeah. Okay. Does anybody know what hexadecimal uses? What that base is? It's close to 6, but what's deci? What's deci mean? 10. So 6, 10, 16. Okay. And hexadecimal. So like when I program things in my website and I want to color it. Okay. A lot of color wheels are hexadecimal. Okay. So they use a series of numbers and then they use a series of letters. That makes sense? Okay. A lot of coding in computer programs and stuff like that are.
On the web about 5 numbers and the use of.
Shut up. She does it all the time. Like, so my wife got me this Apple Watch for my birthday, and like she's listening to everything, and every once in a while, like she'll like record like 5 minutes of what I said, and she'll like read back through it, and none of it, none of it is what I said. Like, either I'm talking different language or.
That's actually so sweet. you know that music.
I mean, they want to listen. They want to listen to me. Like, what are they going to get from me? Like, the government can watch me all they want. I don't care. Like,
they have to learn.
How to walk.
Yeah. Big Brother isn't gaining anything from Mr. Fay, that's for sure. All right. So common logarithms, that's talking about base, the base being 10. All right. If you guys grab your calculator now, you've got varying calculators. So I've got a couple different ROMs here. If you have this calculator, so that's kind of one. It's like the most basic version of like your TI. If you had like a TI-83 and no silver edition or anything like that, this is the RAM that you or the ROM that you would have. And if I go to mode, okay, that's my only screen. That's my only ability. So when I hit log on my calculator, what does it fill in for me? It's automatically base 10. Okay, that is the only thing that operating system will use, and I do not have the ability. If I go, so they hide some other features under math. If I go to math and I scroll through, there are no other places for me to pick up log again. Okay, if I can't remember where things are, I go to my catalog, second 0, and then I'll hit L for log. Where's it at? And I'll scroll through to find log, and you see how it doesn't give me any other options. It's just the common log. Does that make sense? Okay. Now, the more updated operating systems you have, so this one is not going to work. That one. Okay, this is a 2.55 operating system. So this is a little bit nicer because when I go to mode here, you see I have the option to go down here to where it says classic or math print. Okay, so if I'm in math print, so that means it's going to kind of put things in the way that I write them. Now, if I hit log again, it just puts in log. But I do have the ability to go to math here, scroll down, and you see where it says log base. Hit enter. You see what it does for me? It now allows me to change the base without using our change of base formula that you maybe have experienced last year. Okay, we might talk about it again this year. But that will allow me to evaluate like a log base 2 of 12, and then I can use my calculator and give me that value. Okay, so 2 to 3.584962501 will give me 12 back, right? Okay, that's nice. The other calculators, you got your color calculator. If anybody's got that thing. Okay, so that's you're going to go to math again. Yeah. All right, so I'll go to mode. So here it asks, and I haven't dealt with this one a lot. I just found this ROM. If you go down to, okay, I guess the first one, math print is the first one. So then click, go to math again. And I believe then you see log base as still option A there, and it'll do the same thing. Okay. So those are some options for you. Other than that, if you know your calculator is just a little bit more basic than these two, then you're probably only going to have the common log. All right, and that's not going to address things maybe the way you need them to if you're going to use your technology. The thing with GeoGebra, obviously, if I type in log. And then you saw there, it will, when I hit log, it will tell me these are the things that I need to type in. Okay? So this one allows me to change the base, and it allows me to change the argument. This one here just allows me to use an argument. So if I'm just using an argument, what's the base going to be? 10. Here it says log base 10 already. This one's log base 2. So if I go log base 2 of 12, okay, it gives me that 3.58 number I was looking for, right? So those are some things that if you're going to use your calculator with different bases to kind of be aware of. In the past, I've had people just say, well, I'm hitting log, and I'm not getting the same numbers you're getting. It's because your calculator is using the wrong base. All right? That is a huge, 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 huge thing. Now, when I see, just to clarify things for you, when I say like log base 10 of 100, and it just looks that way, okay? I never deal with it that way, okay? Because our definition of a logarithm always incorporates a base, right? So whenever I see that, I rewrite it that way. Because now it's a little bit more visual of what I need, right? 10 to the what will come back and give me 100. 2. So log base 10 of 100 is 2. Why do I talk about that? It's because when we get to this guy, natural logarithm. Okay, you guys remember the natural logarithm from last year, ln? Okay, natural logarithm, okay, by definition says ln of x is equal to log base e of x, meaning that those two things are the same. If I were to graph on my, let's use GeoGebra, ln of x gives me that curve right there, right? Graph log base e of x gives me that thing there. Are they different? No. So ln of x is the same thing as log base e of x. So why do we talk about that? They're going to use ln of x, and it's just easier to write out. It's easier to type out, all that kind of stuff. It actually becomes very convenient for us in calculus. It comes as we start to solve some of our equations that, like principal times e raised to the RT. To solve that for r or t, the natural log is very useful. It's convenient, okay? Because of some of the properties we'll talk about here in a little bit. So a lot of times I just write ln of x. I think because it's more concise, you lose some notation, that there's ambiguity there, there's vagueness. People get confused, they struggle, they see it, and it flips them out. When you see ln of x, if it flips you out, rewrite log base e of x, okay? I've been doing this since I was your age, okay? It flips me out sometimes when I see ln of x. I have to just, by nature, rewrite it as log base e of x, okay? And I think that's a very safe thing to do. It doesn't take a whole lot of time, and it provides a whole lot more meaning, I think, when we do that. All this slide says is, if you have ln of x equals y, if and only if e to the y is equal to x. Now, why does that make sense? Well, think about this. ln of x is the same thing as log base e of x, right? Doesn't the definition of a logarithm say that base raised to that exponent should come back and spit out the argument? Okay. So when I see ln of x equals y, and they change it automatically to e to the y equals x, where does that come from? It comes from the fact that ln of x is the same thing as log base e of x, and then we apply our definition of a logarithm, okay, and change it to an exponential. Is that okay? So that gets us to these rules. And we talked about these yesterday. Okay, but yesterday, if you remember, they were not using ln. So I'm going to do this first one. If ln of 1 equals 0, can I rewrite that as log base e of 1 is equal to 0? Does it make sense that e raised to the 0 power comes back and gives me 1? Okay. Is that the same thing that we talked about yesterday when we said log base a of 1 is equal to 0? A to the 0 is equal to 1? And remember, a was an element of your real numbers, right? A could have been anything. Let me rephrase it. Let's say A is an element of your natural numbers, but A cannot be 1, okay? So really any real number that was positive other than 1, right? Okay, or 0. Well, is E one of those numbers? E is one of those numbers that is A, right? Or that was categorized as the group of A. So E is in there. E is one of these numbers, okay? So then this should apply when I change the base to E. So this thing here is the same thing, same property we talked about yesterday. Does that make sense? Okay. The other ones go the same way. Okay, so if I go ln of E equals 1, well, that's log base E of E equals 1. Well, doesn't it make sense I have to raise E to the first power to get back to E? Well, how does that compare to what we talked about yesterday? Yesterday I said log base A of A was 1. Well, isn't E just one of those A's? Does that make sense, everybody? All right. So what I want you guys to understand and realize, and this is just a snippet of what happens all the time in mathematics. If I don't understand the relationships, I'm going to be forcing myself to try to remember 8 things here. If I understand relationships, I don't have to memorize any one of those. I just memorize or learn the definition of a logarithm. Okay? And that will generate these 8 objects when I need them. Is that all right? Because those 4 and the 4 we talked about yesterday, you're going to mess them up and try to memorize them. You're going to confuse things. A lot of times people say, well, ln E equals 0. Well, no, it doesn't. It equals 1. But you're trying to remember 8 things and how they relate to one another, and that's the problem. Okay? Is that all right with everybody? Okay? Let's see here. And so I'm introducing all these properties. We're going to come back tomorrow and the following day and just start practicing using these things, okay? But there's some information that I think needs to be covered kind of collectively or holistically, and then we'll come back and deal with them and examples. All right. These 3 laws of logarithms. Remember those from last year? Okay. Those laws of logarithms allow us to take arguments that have multiplication in them and expand them as logarithms summed together. Okay? Or it allows us to take logarithms that have division and expand them to subtraction. It allows us to use our kind of a power rule down there at the bottom. Okay? I'm going to spend a little bit of time talking about how we address proving these things and why they are there. I think last year we were just giving them and told, okay, if there's a product, you can expand them to a sum, right? If it was a quotient, you can expand them to a difference. Remember, when it's a quotient, though, and difference, order is important, right? Subtraction is not commutative, so we got to pay attention to that. Addition doesn't matter, but I want to prove that addition one, okay? And then once we prove the addition one, kind of show you how simple the division one would follow from that, or how easily it follows. So we're going to prove that's right, prove log. I'm going to use a different base, m of ab, just because I don't want to use a, lowercase a and capital A. So log base m of a times b is equal to log base m of a plus log base m of b. Okay. Now what happens here, guys, is in this proof, we are going to make some substitutions. Okay. This is just a numerical value, right? That makes sense? So I'm going to say let log base m of a equal x. We can do that. We can always redefine our variables as long as we state what we're redefining them as, right? So I'm going to let a complex thing just become x. Okay? And I'm also going to let log base m of b equal y. Is that all right? Now, would you guys agree that if I look at, let's see here, look at just that one right there, can we write that m to the x is equal to a? Okay? And if we look at this one here, we write m to the y equals b. On a proof, we always like to talk about y. definition of logarithm, right? Okay, it was, sometimes you write the definition out, sometimes you write like now, and then write because, if a to the x equals y, then log base a of y equals x, something like that, okay? But that's all encapsulated in our definition, if we know what that means. All right, so that's nice. What did we do right here? What are we doing with A and B? What operations happen with A and B right here? Multiplication. So let's multiply A and B down here. So I multiply A times B. What's another way of writing A times B right now? Okay, m to the x times m to the y, right? What's another way of writing that? Good, m to the x plus y. If I had, say m was 2, x was 3, y was 4, you'd write that as 2 to the 7th, right? Okay. So when I'm multiplying like bases, I add the exponents. Okay. So AB is the same thing as m raised to the x plus y. Okay. We know that let me write it this way, the logarithm of a base of some argument is equal to y if and only if a to the y is equal to x, right? This right here is of that form, isn't it? Let's put it back into logarithmic form. Let's apply the definition in reverse order here. Okay? So my base, so I'm going to change this. I'm going to write the word then. So this m is my base, right? Okay? So I'm going to write the word log. M is my base. Okay? Now y, okay, that y, that exponent would be this thing right here, correct? Okay? So over here in my rule, my definition, that y goes to the right-hand side. So I have x plus y. Is that right? And then x over here becomes the argument there, right? So x, for this particular case here, would be the AB. Does that make sense to everybody? Okay. So we're just kind of applying the definition of a logarithm to our AB equals m to the x plus y. Is it okay? So now look at that. I've got, in that last line, I've got what we have up in the blue line on the left-hand side, right? I got log base m of a times b equals now x plus y. Well, what was x? Log m of a. What was y? Yeah, so can I substitute those back in? Log base m of a, and then log base m of b, and we're done. Okay? Because that gets us to that statement that we're trying to prove, right? That is an algebraic proof, guys. That is when you get to higher levels of math, they're going to ask you to do. And I would, granted, I was the only one in my high school class that went on to be a math teacher. Okay? So I don't know how many of you are going to go get math degrees. Now, I know there's other people that I graduated that went math routes or engineering routes, that kind of thing. Okay, so they use this. They were in higher level math classes. But when you get to those higher level math classes, this is a lot of the math that you're doing. Okay, it's not so much story problems and trying to find concrete values. It's doing proofs like this and trying to recognize and understand why the things that we've been taught early on in our lives work. Okay, that's the reason why that one works. Now, here's my question: how does that differ from A divided by B? If I take, and I'm kind of running out of room here, but we should do it right here. If I have log base m of A divided by B, obviously we're seeing that that's going to be called log base m of A minus log base m of B, right? Well, think about this. If I let, obviously, x equal log base m of A again, and let y be log base m of B, eventually I will have something like this where it says A over B is equal to x. Sorry, A over B will eventually. So I let A, I'll do the definition. So I'll get A equals m to the x, and B equals m to the y, right? But then when I do division, I would have m to the x over m to the y, right? Well, is that the same thing as m to the x times m to the negative y? Does that make sense? When I have a denominator here, if I want to put that in the numerator, I just make the exponent negative. Well, if I did that, doesn't that give me m to the x minus y? And you see then eventually that thing there, if I were doing division, that thing becomes x minus y, and then when I substitute log A and log B back in, I get log MA minus log MB. Okay. Tomorrow we'll start, and I don't think we're going to have enough time to finish that third wall, but tomorrow maybe we'll go through and prove that, and then start doing an example, start using these problems. I think last year, probably what you guys did the most was this example, something like this. If I have log base 4 of 2 plus log base 4 of 32, can I rewrite that to sum, right? And those properties are two-way streets. So you can start with the sum and go to a product, or start with the product and go to a sum. So can I rewrite this as log base 4 of 2 times 32? Now, understand your vocabulary. It says evaluate, right? What's the key word in evaluate? Value, right? You're going to get a number back, okay? So I get log base 4. Does this turn into 64 as my argument? So now let's use our definition of a logarithm. 4 raised to the what should give back 64. 4 times 4 times 4 times 4 times 4 times 4. How many of those do I need? I need 3. So 4 to the third gives me 64. So log base 4 of 64 is 3, meaning that thing right there would have been 3, right? Does that make sense? Okay. Can I go log base 5 of 2 plus log base 4 of 32 and get the same thing? I heard it over there in that room. They said no. Okay. So your bases have to be the same to apply these rules, right? Okay. If we go back to the definition that we're doing, the proof that we're doing, the bases were all m, right? That's the only way that works. So if I have different bases, I just leave it alone. I can't condense it or expand it, whichever version I need to do. Like I said, tomorrow we'll spend a little more time on these. Do a handful of examples, and maybe towards the end of tomorrow's class, we start to see our first couple of equations. All right. My goal today is to, at some point, do a parabola video and get that posted, and then probably on the weekend, knock out the other 3, get those posted for you. No, I'm not a loser.